Okay, I hope I'm audible to all students who are attending this lecture of Mathematical Methods for Economics, Part 1. I intend to start with a new topic today in this course, which is single variable optimization. Okay. I intend to start with a new topic within the MME1 course. This is single variable optimization. Formally, this is chapter 9 of the book I prefer to follow for this course, which is Sater and Hammond. Okay, this is the book I prefer to follow for this course, the 4th edition. Okay, now all students can recall that in the previous lectures when we were talking about continuity, derivability, okay, we had also done the continuity and derivability theorems. Okay, now we will be digging deeper into optimizing. So we are now interested in finding out as to what is the maximum value attained by a given function in a given domain, what is the point of maxima. Similarly, what is the minimum value attained by a function in a given domain, what is the point of minima. We will also look at the curvature of the function. Is it concave, is it convex, is it strictly increasing, strictly decreasing. Okay, so let's look at all these concepts within our lectures on single variable optimization. Now, first let's talk about the concept of strictly increasing function. When do we say that a function is said to be strictly increasing? Okay, so let's look at the definition of a strictly increasing function. The function f is said to be strictly increasing. The function f is said to be strictly increasing on the interval I if and only if for x1 and x2 belonging to the interval I, x1 less than x2 implies f of x1 is less than f of x2. So clearly this is the definition of a strictly increasing function. A function f is said to be strictly increasing on an interval I if for two values of x lying in this interval, say x1 and x2, if x1 is less than x2, it implies f of x1 is less than f of x2. And then guys, we can look at the definition of a strictly decreasing function. So let's quickly look at the definition of a strictly decreasing function. Okay, the function f is said to be strictly decreasing. The function f is said to be strictly decreasing on the interval I if and only if for two values of x lying in the interval I, if x1 is less than x2, it implies f of x1 is greater than f of x2. Okay, so you can clearly see that a strictly decreasing function is just the opposite of strictly increasing function. We say that the function f is said to be strictly decreasing on the interval I if and only if for two values of x lying in the interval I, x1 less than x2 implies that f of x1 is greater than f of x2. Okay, so hoping that students have understood this. Now, students should also know the definition of increasing and decreasing. So, if I talk about increasing, if I just talk about an increasing function, if I just talk about an increasing function, so the definition of that would be the function f is said to be an increasing function. The function f is said to be an increasing function on the interval I if and only if for two values of x belonging to the interval I, x1 less than x2 implies f of x1 is either less than or equal to f of x2. So when we talk about an increasing function, it also includes the possibility of f of x1 being equal to f of x2. So look at this, guys. When I talk about a strictly increasing function, strictly increasing means x1 less than x2 implies f of x1 is strictly less than f of x2. Whereas if I talk about an increasing function, x1 less than x2 implies f of x1 is either less than or equal to f of x2. Similarly, let's look at the definition of a decreasing function. Let us look at the definition of a decreasing function. And then we can compare it with strictly decreasing function. So I can write the function f is said to be a decreasing function. The function f is said to be a decreasing function on the interval I if and only if for two values of x belonging to the interval I, we have the following equation: x1 less than x2 implies f of x1 is either greater than or equal to f of x2. So again, guys, if you compare a strictly decreasing function with a decreasing function, in strictly decreasing function, my implicative statement is x1 less than x2 implies f of x1 is strictly greater than f of x2. But if you compare it with the decreasing function, the implicative statement is x1 less than x2 implies f of x1 is either greater than or equal to f of x. That means in the case of increasing and decreasing function, the possibility of equality also exists, unlike strictly increasing or strictly decreasing function. So hoping all students have understood these four definitions, which you can see on your screens. Okay, now we can draw diagrams. Let's look at these diagrams which make it even more clear. So 4 diagrams I am drawing on the screen, and all these 4 diagrams represent strictly increasing and strictly decreasing functions. Okay, so as you all can see on your screens, these are the 4 diagrams. Okay, we have x-axis, we have f of x. In all the diagrams, we have x and f of x. Okay. And now look at the first diagram. You can clearly see that this is my, suppose in all the cases, guys, this is my domain. Suppose this is my interval I. In all the 4 diagrams, I am drawing the interval I. It's a closed interval. And you can clearly see, suppose I draw a function like this. You can clearly see it's strictly increasing and convex. If I take two values, x1 and x2, then x1 less than x2 implies f of x1 is strictly less than f of x2. So this diagram A is the case of strictly increasing and convex. You can clearly see that the graph is convex to the origin. Similarly, I can draw another diagram. Look at the second diagram, guys. Again, you can see I take two values, x1 and x2, and you can clearly see this is my f of x1, this is my f of x2, and you can clearly see that x1 less than x2 implies f of x1 is strictly less than f of x2. Again, you can see that this is the case of strictly increasing and concave. So strictly increasing and concave. You can see in diagram B, the graph is strictly increasing and concave to the origin. Similarly, guys, diagram C. Now look at this. Suppose this is my graph. Now you can clearly see x1 less than x2 implies that f of x1 is strictly greater than f of x2. x1 less than x2 implies f of x1 is strictly greater than f of x2. So this is the graph of a strictly decreasing and convex function. So diagram C represents a strictly decreasing and convex function. And similarly, look at graph D. Again, you can see that x1 less than x2 within the domain implies that f of x1 is strictly greater than f of x2. Again, you can see that in diagram D, the graph is strictly decreasing but concave. Strictly decreasing and concave. So I hope students attending this lecture have understood these 4 diagrams. The first diagram represents the case of a strictly increasing convex function. Second diagram represents the case of a strictly increasing concave function. The diagram C represents the case of a strictly decreasing convex function, and diagram D represents the case of a strictly decreasing concave function. So I hope that students are clear with this. And then guys, if I draw a function like this, for example, suppose you can see I am drawing another function. This is x and this is f of x. And you can see now I am drawing a function. So clearly look at this function y equal to f of x. Now I ask students, is this a strictly increasing function? Is this a strictly increasing function? No. Because suppose my interval is from here to here. Suppose this is my interval I, it's a closed interval. You can clearly see in this interval I, if I take 2 points here, x1 and x2, clearly, what do you see from the diagram? x1 less than x2, but x1 is less than x2, but f of x1 is exactly equal to f of x2. If you look at f of x1 and f of x2, they are exactly the same. That means this function is not a strictly increasing function. Therefore, the above function is not a strictly increasing function. It is just an increasing function, but not strictly increasing. Similarly, I can draw another graph. Suppose this is x on the horizontal axis and f of x on the vertical axis. Suppose I have a function like this. Suppose this is the graph of y equal to f of x. Now again, suppose this is my closed interval I. Again, you can see if I take two values x1 and x2 in the domain, clearly from the above diagram, x1 less than x2, but you all can clearly see that f of x1 is equal to f of x2. From the diagram, all students can clearly see that even though x1 is less than x2, but if you look at the image of this, f of x1 exactly equals f of x2. Therefore, we can say that the above function is not a strictly decreasing function. The above function is not a strictly decreasing function. It is just a decreasing function, but not strictly decreasing. Okay, so I hope students have understood this. Now, we have done the definition of strictly increasing and decreasing. Let us now look at the criteria. Now, guys, whenever I talk about criteria in my MME lectures, it means that is the way we show it in the numericals. How do I show whether a function is strictly increasing or decreasing? We have done the definition. But now let's look at the criteria. The criteria will help us to solve questions based on strictly increasing and strictly decreasing. So our heading now is criteria for strictly increasing or strictly decreasing function. Criteria for strictly increasing or strictly decreasing function. So let the function f be derivable. Let the function f be derivable on the interval I. Then f dash x strictly greater than 0 for all x belonging to the interval I implies that f is strictly increasing. F is strictly increasing on the interval I, whereas f dash x strictly less than 0 for all x belonging to I implies that f is strictly decreasing on the interval I. So guys, this is the criteria for strictly increasing or decreasing. What we had done in the beginning of this lecture was the definition of strictly increasing or decreasing. What we are doing right now is the criteria using which we will show whether a function is strictly increasing or decreasing. So in my lectures on single variable optimization, students should be able to know the difference between the definition of a concept and its criteria. If I ask you to define strictly increasing or decreasing function, you will refer to the definition I have taught you. But if a question asks you to show whether a function is a strictly increasing or decreasing function, you will show it by using this criteria, which you can see on your screens. That means for a function f which is derivable on the interval I, If its first order derivative is strictly greater than 0, we say that the function is strictly increasing on the interval I. If the first order derivative is less than 0, we say that the function is strictly decreasing on the interval I. Okay, hoping students have understood this and have no doubts. Then guys, let's look at another definition. This is the definition of maximum and minimum point. This is the definition of maxima, minima. Okay, so let the function f of x have the domain capital D. Let the function f of x have the domain capital D, then the point small c belonging to the domain capital D is a maximum point. It is a maximum point for the function f if and only if f of x is less than equal to f of c for all x belonging to the domain D, and small d belonging to capital D is a minimum point. It is a minimum point for the function f if and only if f of x is greater than equal to f of d for all x belonging to the domain D. If all students can recall, in our lectures on continuity and derivability theorems, we had also done this by the name of extreme value theorem. If all students can recall, in our lectures on continuity theorems, we had done something called the extreme value theorem. If the function is continuous on a closed interval in the domain, then there exists a point C belonging to the domain capital D, such that C is called the point of maxima and f of C is greater than equal to f of x. F of C is called the maximum value. Similarly, there exists a point small d belonging to the domain capital D, which is called the point of minima, and f of x is greater than equal to f of d, so f of d is called the minimum value. So I can write where f of c is called the maximum value, f of c is called the maximum value, and f of d is called the minimum value. F of c is the maximum value and f of d is the minimum value. Okay, then guys, we can even write a note. So I am erasing the initial part, the criteria part, and let's write a note. Erasing the initial part, let's look at this particular note. Okay, so the note is as follows. The note is as follows. If f of x is strictly less than f of c for c belonging to the domain D, then C is a strict maxima. Then C is a strict maxima. Similarly, guys, if f of x is strictly greater than f of d for the point D lying in the domain capital D, then we say that D is a strict minimum. D is the strict minimum. So guys, if you read this and if you read this, What do we learn? Small c is called a point of maxima if f of x is less than equal to f of c. But if f of x is strictly less than f of c is called a strict maxima. Similarly, D is called a point of minima if f of x is greater than equal to f of d. But if f of x is strictly greater than f of d, then D is called a strict minimum. So, hoping that all students have understood this note and have no doubts. Guys, if I erase the definition on the bottom part of the screen, we can write another note. Okay, we can write another important note relating to this particular concept, which is as follows. So the third note is that if the point C maximizes the function f in the domain D, I repeat, if my point C maximizes the function f in the domain D, then it minimizes minus f in the domain D. That is, if f of x is less than equal to f of c, okay, for all x belonging to the domain D, then minus of f of x is greater than equal to minus of f of c for all x belonging to the domain D. Now, what is the third point telling you? The third point is telling you if C is the point of maxima for the function f, it will be the point of minima for the function minus of f. That means if I have a function f and if I plot the negative of that function, then if C is the point of maxima for f, it will become the point of minima for minus f. So hoping that students have understood this definition and have no doubts. Okay. Now we can look at the concept of stationary points. So erasing all this, let us look at another definition. Definition to calculate stationary points. Now, stationary points are those points which lie in the interior of the domain, and they can either be the point of maxima or they can be the point of minima. So let's look at the definition of stationary points. Consider a function f of x. Consider a function f of x. Then x0 is a stationary point. X0 is a stationary point for the function f if the derivative f dash at x0 is equal to 0. Okay, so we have been doing this very often even in the high school mathematics. How do you maximize or minimize a function? First of all, what do? You find the stationary points, right? Now, how do we find the stationary point? Put the first order derivative equal to 0 and solve for x. This is what students have been doing even in high school mathematics. You differentiate the function and you put it equal to 0. You solve for x. The value of x you get is nothing but the stationary point. Now that stationary point can be a point of maxima or it can be a point of minima. So you can see this, guys. I'm drawing two diagrams on the screen. This is x, this is f of x. You can see I've drawn a function You can see that there is one stationary point which is x0. Okay, this is my point x0 comma f of x0. Okay, if I draw a tangent at this point, what is the slope of this tangent, guys? The slope of this tangent, is nothing but f dash x. And you can see that the tangent is parallel to the x-axis. Mathematically, any line parallel to the x-axis has slope equal to 0. That means at the point x0, the slope, which is f dash x0, is equal to 0 because the tangent is parallel to the x-axis. Clearly, you can see that x0 is the point of maxima and f of x0 is the maximum value. If I draw f of x0, this is the maximum value. And on similar lines, I can draw another diagram. On similar lines, we can draw another diagram. This is x. Okay, this is f of x. And you can see I am drawing another graph on the screen. Okay, you can clearly see this is my point x0 and this corresponds to x0 comma f of x0. You can clearly see if I draw a tangent at this point, again you can see that this tangent is parallel to the x-axis. So f dash x0 is equal to 0. Clearly in this case, x0 is the point of minima and f of x0 is called the minimum value. F of x0 is called the minimum value. So guys, you can clearly see in the first diagram, the function is strictly increasing. If I also combine the concept of strictly increasing and decreasing, before x0, the function is strictly increasing. After x0, the function is strictly decreasing. Similarly, all of you can see that in the second diagram, this is diagram A, this is diagram B. In diagram B, you can clearly see to the left of x0, the function is strictly decreasing, and to the right of x0, the function is strictly increasing. So hoping that students have understood this and have no doubts. Okay, so guys, using this we can now write the first derivative test for maxima and minima. So all students can write this first derivative test for maxima, minima. So let's look at this first derivative test. Okay, let's find the point of maxima, minima using the first derivative test. So within this, the first point, if my function is an increasing function for x to the left of c and the function becomes a decreasing function to the right of x equal to c, then we say that x equal to c is a point of maxima. It is a point of maxima for the function f. And similarly, we have second point which says that if f dash x is decreasing for x to the left of C, and if my f dash x is increasing for x to the right of C. Now in that particular case, we say that x equal to C is a point of minima. It is a point of minima for the function s. Guys, the same thing you can see in the diagrams as well. Whatever first derivative test I have written, you can see it in the diagram as well. For values of x to the left of x0, the function is strictly increasing. For the value of x to the right of x0, the function is strictly decreasing. So I say that x0 is the point of maximum. Similarly, in diagram B, for values of x to the left of x0, the function is strictly decreasing. For values of x to the right of x0, the function is strictly increasing. So we say that x0 is the point of minimum. Same thing I have written in point form as the first derivative. If the derivative is positive to the left of C and negative to the right of C, x equal to C is the point of maxima. If the first order derivative is negative to the right of C and positive to the, if the first order derivative is negative to the left of C and positive to the right of C, we say that x equal to C is the point of minima for the function f. So hoping that all students have understood the first derivative test and the concept of stationary points. Okay. Okay. So now after having done the concept of stationary points and the first derivative test for maxima and minima, we now look at the method for finding the extreme points. That means we now look at the method for finding the point of maxima or minima in a closed bounded interval. So our heading now is method of finding the extreme points. Method of finding the extreme points. Now when I say extreme points, it means point of maxima or the point of minima. So method of finding the extreme points on a closed and bounded interval. Okay, so let's look at the following method on how to find maxima or minima in a closed bounded interval. Okay, so first of all, step number 1. So suppose guys my closed and bounded interval is A to B. Suppose my closed and bounded interval is A to B. Then step 1. Step 1, find all the stationary points. Find all the stationary points of the function f in the open interval A to B. That is, find all points x belonging to the open interval A to B such that the first order derivative f dash x is equal to 0. So this is step 1 guys. We are given the function f of x. You find the derivative f dash x. You put it equal to 0. You solve for x. You get all the stationary points. Remember, stationary points lie in open interval A to B. They lie in the interior. Step 2. Step 2. Evaluate the function Evaluate the function f at the end points. Evaluate the function f at the end points a and b of the interval, and at all the stationary points, obtained in step 1. So I am revising step 2 again. In step 1, we have found out all the stationary points. Now, what are we doing in step 2? In step 2, we are evaluating the function at the endpoints A and B. So we are finding f of A, f of B, and we are also evaluating the function f at the stationary points which are obtained in step number 1. Okay, so then comes step number 3. The largest function value obtained in step 2, the largest function value obtained in step 2 is the maximum value of the function f in the closed interval a to b, and the minimum value, or I can say the smallest function value obtained in step 2 is the minimum value of the function f in the closed interval a to b. Okay, so I hope students have understood step 3. So guys, I am revising all these steps with you again. What is the objective? Objective is to find the point of extrema. When I say extrema, it means either a maxima or a minima. So we need to find the point of extrema in a closed bounded interval a to b. Our step 1 is, first of all, we find all the stationary points of f. Now students know how do we find the stationary point? Put the first order derivative equal to 0 and solve for x. Step 2, you evaluate the function at the end points a and b, as well as at all the stationary points you have found in step 1. And step 3, whatever maximum value you obtain in step 2, that is the point of maxima. Whatever minimum value you obtain in step 2, that gives you the point of minimum. So after having theoretically understood this, let us do a practice question, and then we plan to stop for this lecture. So let's look at this particular practice question. Find the maximum and the minimum values of the function f of x equal to 1 upon 9x cube minus 1 upon 6x square minus 2x by 3 plus 1, where x belongs to the closed interval minus 3. Okay, so we need to find the point of maximum and minimum. We need to find the point of maxima and minima for this given function, okay, on a closed bounded interval. So guys, step 1, First, let's find f dash x. If I differentiate it, what do I get? 3x square by 9 minus 2x by 6 minus 2 by 3 equal to 0. I can further solve this. I can take 1 upon 3, I can take common. So inside, what do we get? So basically, this is 3, 3s are 9, 2, 3s are 6. So if I take 1 upon 3 common, so we are left with x square. We are left with x square minus x minus 2 equal to 0. X square minus x minus 2 equal to 0. This is what I get when I take 1 upon 3 common. Now guys, we can do the middle term splitting. So x square minus x minus 2, if I further solve, I can get x plus 1 into x minus 2 by using the middle term splitting method. Put it equal to 0. So guys, what are the stationary points we get? Therefore, if I solve the above equation for x, our stationary points are x equal to minus 1 and x equal to 2. You put x equal to minus 1 in this equation, you get it 0. You get x, you put x equal to 2 in this equation, you get f dash x 0. So my stationary points are minus 1 and 2. Now I can make an analysis table here. Okay, so on the, so we have critical points, we have critical points, and we have the value of the function at those points. So guys, first of all, I will evaluate the function at x equal to minus 3, x equal to plus 3. These are my endpoints. Then I will evaluate the function at minus 1 and at 2. These are my stationary points. Now, can we quickly evaluate the function at all these points? So put x equal to minus 3 in the function. So clearly you can cross check guys, f of minus 3 comes out as minus 3 by 2. That means you put x equal to minus 3 in the function, you get f of minus 3 as minus 3 by 2. Similarly, you can check that f of plus 3 is going to come out as half. F of minus 1 is gonna come out as 25 by 18. If you put minus 1 in the function, you get 25 by 18. And if you put 2 in the function, so f of 2 is coming out as minus 1 by 9. So guys, these are the values we are getting. When we put all the critical points in the function, these are the values we are getting. Now clearly, if I ask you what is the maximum value, 25 by 18 is the maximum value. I can write this is my max value. So x equal to minus 1 is the point of, it is the point of maxima. It is the point of maxima. And what is my minimum value, guys? My minimum value is nothing but minus 3 by 2. You calculate minus 3 by 2, it's minus 1.5. This is my minimum value for the function, and I can say that x equal to minus 3 is called the point of minimum. X equal to minus 3 is called the point of minimum. So I hope that all students have understood this question. Step 1, find the first order derivative, put it equal to 0, get the stationary points. Step 2, evaluate the function at the endpoints and at the stationary points. Step 3, the function which gives us the maximum value gives us the point of maxima, which is x equal to minus 1. And the function with the minimum value gives us the point of minima, which is x equal to minus 3 for this question. So guys, this is where I intend to stop in this particular lecture. Okay, the objective was to make students familiar with the concept of strictly increasing, strictly decreasing, increasing and decreasing functions, as well as the concept of maxima and minima in a closed bounded interval. Now in the next lecture of single variable optimization, we will talk about the concept of local maxima and minima. What we have done today in the lecture is absolute maxima and minima. In the next lecture, we shall be speaking on local maxima and minima. So I stop here. I hope all students have enjoyed this lecture. Any doubt, you can unmute your mics and ask, or you can call up, or you can mail me your doubts. You can mail me your doubts at the following email ID. Okay, students can also mail me their doubts at the following email ID. So guys, this is where I intend to stop in this particular lecture.